Hi all, in this video we are going to discuss about audio embedding of future and future extraction as well as clustering. So for that let's import required libraries. So where we will be using NumPy and Pandas for handling numerical operations and data frames, and Librosa for process audio signals, extracting features like MELs, spectrograms, and so on. So visualizing tools like Matplotlib and Seaborn for plot results. So clustering and dimensionality reduction, we are going to use TMAP, TSNE, and UMAP. And as well as hierarchical clustering are used for clustering and visualizing high dimensional data. So for visualization, we are going to use Silhouette score, which measures clustering quality. By ensuring these libraries are loaded, our project's gonna leverage a complete toolkit for processing and clustering audio data. So basically, we generate 5 synthetic audio signals to simulate a realistic dataset. Each signal is a sine wave with a unique frequency ranging from 220 Hz to 660 Hz. So using Librosa, we extract MEL spectrograms, which represent audio features in a format suitable for analysis. So basically, these spectrograms are converted to decibels for clarity, and the mean values across time are aggregate as feature vectors. So the final feature matrix has dimensions of 5, 40. So where each row corresponds to a signal and each column represents a MEL band. This synthetic dataset mimics real-world data, ensuring a controlled environment for testing clustering methods. So moving on to dimensionality reduction using UMAP. So basically UMAP reduces the 40-dimensional MEL feature space into 2 dimensions, preserving the structure for clustering and visualization. Therefore, the parameters like n neighbors and min dist control how UMAP balances local and global structure. So the resulting embeddings, which is going to be 5 cross 2 matrix, are visualized as a scatter plot, showing the relative position of each audio sample in reduced space. This step simplifies clustering by making the data more interpretable while retaining meaningful relation. So let's move on to k-means clustering. So using k-means, the reduced data is grouped into 3 clusters. Okay. So k-means works by iteratively assigning samples to clusters based on proximity to the centroids, recalculating these centroids until convergence. So the output is a cluster label for each audio signal representing its group. This step provides the output and as well as provides a foundational clustering solution, helping separate signals based on their MEL spectrograph features. So let's move on to visualizing these cluster sizes. So these cluster sizes are calculated to understand the distribution of sample across clusters. A bar plot visualizes the number of audio signals in each cluster, as discussed before, and also ensures clusters are meaningful and provides insightful to diversity and similarity. So the cluster centroids in UMAP space represent the average feature values of each cluster. So by plotting these centroids, we gain insight into the difference between cluster in terms of their reduced features. So this step basically reveals how clusters differ and helps interpret their composition. And moving on to hierarchical clustering. So this organizes the data into dendrogram. A tree-like structure is showcasing how samples are merged into clusters step by step. Using the award method, this step identifies relation between clusters, providing a complementary view to k-means clustering. And next, moving on to calculating the Shilloti score, which measures clustering quality by evaluating how well samples are separated. The score will range typically from -1 to 1, where higher values indicate better defined cluster. This step provides a quantitative metric for assessing clustering results. In our case, the score is around 0.12. And let's moving on to dimensionality reduction using TSNE. So TSNE provides another dimensionality reduction method complementing UMAP by preserving local relationships. TSNE or the SNE helps visualize clusters with a different perspective. The scatter plot highlights how clusters group in this reduced space. So further validation of clustering approach. So moving on to enhanced visualization. So here the bar plot summarizes the cluster sizes and heat map of clustering of centroids for future differences, as well as pair plots to explore relation between reduced dimensions. So this visualization in general improve the interpretability of cluster results and offer a comprehensive view of cluster properties. And moving on to analysis. So this analysis plots the Shillot's coefficients for each sample, showing its contribution to clustering quality. Samples within well-defined clusters have higher coefficients, and while those near cluster boundaries have lower scores. So this visualization highlights the effectiveness of clustering. And let's moving on with principal component analysis. Using PCA, high-dimensional data is projected into two components, providing another view of clustering. So the plot includes explained variance showing how much information the PCA retains. So this step validates the clustering structure further. So moving on to parallel coordinate plot. So parallel coordinates visualize future values across dimensions for each cluster. Each line represents a sample and the clusters are color coded. So this plot highlights feature trends and differences across clusters, improving interpretability. So that's all. Thank you.